First thing you want to do is interpret what it's asking. So when you see, again, this integral symbol with the numbers there, that means the definite integral. And like the one above, when it's above the x-axis, it's all positive. It's the same as the area. So you want to identify the region first, and drawing a picture can help do that. So the square root of x is your function, and that's the parent function. It looks like this. And you're going from 1, which you can call that 1, and just come over here and call that 9. So because, as you'll learn here in a second, because this is entirely above the x-axis on the interval from 1 to 9, the definite integral in this case does give you the area, but it doesn't always. What it does always give you is the net accumulation. But in here, we're accumulating positive y values times widths, which is accumulating area. All right, this one said to use 3 subintervals. So for this one, you just want to draw 2 lines, and it doesn't have to be perfectly spaced, but this ends up being your delta x, and it is uniform. So we need to find it. So remember, the formula is just figure out your width, b minus a, all over the number of subintervals you're using, which is 8/3. So that's the width of each interval. Now you need to get your x values marked out. So we're starting at 1, add 8/3 to 1, and you get 11/3. Add another 8/3, you get 19/3. And add another 8/3, and you get 27/3, which is 9. So those are your x values. Now your y values, of course, are going to be the square root of 1, the square root of 11/3, the square root of 19/3, and the square root of 9. Now, if you want to draw this picture every time, I would recommend copying that. So let's go ahead and use it for the left Riemanns. The left Riemanns, if you draw them on the first interval, second interval, third interval, using the y value at the left endpoint. So you should be drawing lines from the left all the way across. And you can tell that's going to be an under approximation, and it's because the function is increasing. So here's what we'll say then. We'll say then the integral from 1 to 9 of the square root of x dx is approximated by, and then we'll say r sub 3, which equals. Now we can factor out the delta x, right? It's uniform. We created it, so 8/3 times, and now we just add up. Oh, I did left, yeah, left Riemann sum. Sorry, I called it r up here. That should be L. There we go. So you're going to use f of 1, f of 11/3, and f of 19/3. So I'm not even going to write f of, because it doesn't really have the name f equals. It's just the square root of. So it's the square root of 1 plus the square root of 11/3 plus the square root of 19/3. And we'll treat this like a free response. So that's width times height plus width times height plus width times height. I'm not going to simplify that. We'll just pretend that's a free response. You're done. And then you would say something like this under approximates the integral from 1 to 9 of the square root of x dx, because, and for rectangles, it always has to do with increasing, decreasing, because y equals the square root of x is increasing on the interval from 1 to 9. It might ask you to justify on a free response. Increasing. All right, if you paste the picture, now you can draw what the right Riemann sum is. So for the right Riemann sum, now you're using the right justified y values. So you have to come back to the left and draw it. And immediately when you draw, you can tell it's going to be too big. So here's what we could say. The integral from 1 to 9, square root of x dx is approximated by r sub 3, which equals, and again, the width is uniform, so 8/3 times the sum of the 3 y values. Make sure you're applying the function to them. So it's the square root of 11/3 plus the square root of 19/3 plus the square root of 9. And there's really no reason to go past that. Width times height plus width times height plus width times height. The width's factored out. And then you could say this over approximates the integral from 1 to 9 square root of x dx, because, and it's the same reason, because y equals the square root of x is increasing on the interval from 1 to 9. So all rectangles have to do with increasing or decreasing. Is increasing. Now, if you'd already done A and B and it happened to ask you for the trapezoidal, then you could just average those two values. It'd be a little bit of writing, but you can manage it. So I'm not going to average those two. I want you to kind of know how to do it from scratch because it might just ask you for the trapezoid. So here we'll paste our picture. And for the trapezoids, you just connect the endpoints there, there, and there. And you can tell it's going to be an under. So your notation, it would be, again, the integral from 1 to 9 of the square root of x dx approximated by t sub 3, which equals. Now, because 8/3 is uniform, we can still factor it out. But for trapezoids, we can always factor out a 1/2 as well. So it's going to be a 1/2 times delta x, and then times. And now all you got to do is double the two y values in the middle, and then add up the ones on the end once. So the trapezoid, you're using all of them if you do it this way. So it's going to be the square root of 1 plus 2 times the square root of 11/3 plus 2 times the square root of 19/3, and then plus the square root of 9. But if you don't want to do that, or if delta x is not uniform, you can still just do trapezoid, trapezoid, trapezoid. If you prefer that. Now for this one, you would say that it's going to be very similar. So if you want to copy this over or under approximation from part A, so I don't have to write so much. It is going to be an under approximation, but it's for a different reason. It's not because y equals square root of x is increasing on that interval. It's because y equals square root of x is concave down. Yeah. C down. So because when you do the trapezoidal, again, remember you're doing secant lines. And secant lines are always on the opposite side of the curve from tangent lines. And by our second derivative test, that's going to be determined whether the function is concave up or down. Okay. And there it is. So those are the three methods when you create your own delta x. But that's not always the case. Okay. So let's jump down to, I want to jump down to example 10. Okay. Going a little bit out of order here. It says f is a continuous function such that f of x is greater than 0 for all x. Nice. Selected values are given in the table above. Part A, approximate the integral from 0 to 3 using numeric methods as indicated by the data. So it won't be that vague. It won't say just use numeric methods. It'll say using a left Riemann sum, using a right Riemann sum, or using a trapezoidal sum, or it could even say using a midpoint sum. We're going to practice all of them so that we'll be ready for any of them. Now, the first thing you want to do when you're asked to find that is go up to the top and calculate your delta x all the way across. So here's what that's going to look like, or how you can do it. From 0 to 1/2 is 0.5. So what I do is I just draw a line from one interval to the other, and I write the width of that interval right above that middle line. And then from 1/2 to 1, that's another 0.5. From 1 to 1.5 is another 0.5. 1.5 to 2 is 0.5. And we keep going. 2 to 2.5 is 0.5. 2.5 to 3 is 0.5. Okay. So because we're going from 0 to 3, and that's what that says on the integral, from 0 to 3, we're going to use all the data points because my leftmost point is 0, my rightmost point is 3. Now notice it didn't tell us how many subintervals to use. When it doesn't tell you how many subintervals to use, it might just say as indicated by the data. You'll always have as many subintervals as you have delta x's. So how many 0.5s did I calculate there? 6 of them. So we're going to use 6 subintervals, okay, for the left and right. All right, so for part A, here's what we could do. If you want to call this definite integral like capital I for integral, So you don't have to write it every time. This is a legal move, right? You can call it I, just do it up top. And now we can say I is approximated by, instead of the integral from 0 to 3, f of x dx. It's less writing. It's approximated by, what do you want to do? Left, right, first? Okay, left it is. L sub what? How many subintervals do we say? 6 equals, you got the squiggles. And now, because delta x is uniform, you can factor out the 0.5. And now, because it's left justified, we add up the first 6 left values. So left, 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 oops, left, and left. So what I'm doing is I'm going from the middle of there, and I'm using the value on the left. But you don't even have to draw that. Just know that if you're doing the left endpoint, it's left justified, and we're not using the last one. Now notice this is easier than if you had the equation, right? Because you don't have to plug in the x values to generate the y values because you're staring at them, right? So it's just 2 plus 4 plus 6 plus 7 plus 4 plus 1. This is a 2 for 1. That's a numeric answer on a free response, and it also indicates your method. So what does it mean to indicate the method? Every single number in your expression appears in the chart above, okay? So as you're writing down your values from left to right, don't try and add stuff in your head. Like don't say, oh, well, the first 2 are 2 and 4, that's a 6. Because if you put down a 6 instead of a 2 plus 4, you're no longer indicating your method, and you're gonna have to go back above there and write f of 0 plus f of 0.5 and then plug in. Yucky, yucky, gross, gross, right? So when you have numeric methods like this, it's actually really, really easy if the delta x is uniform. Factor it out, add up all the values. I have 6 subintervals. I have 6 y values in my brackets. It looks good. You want to add those up and divide it by 2? I don't either. Okay, good. The next one, we'll do the integral as approximated by r sub 6, which is going to again be delta x factored out. But now I'm going to add up the last 6 y values and skip the first. So that's what I like to write justified. So I'm going to skip the 2 and then go from left to right. 4 plus 6 plus 7 plus 4 plus 1 plus 5. Now, some people ask, can we just start on the right and add up the first 6 from the right to the left? Yeah, that's fine too. Just know what you're doing, right? Left justified, right justified. And that's it. That indicates your method, and it's a numeric value. So it's a 2 for 1 on a free response. Let's look at the trapezoid next. The integral can be approximated by t sub 6, which is 1/2 times delta x is uniform, which is 0.5 or another 1/2. And now we add up all the values, except we double the ones on the interior. So the 2 on the outside and the 5 on the outside are just added once. So again, indicating our method, it's 2 plus 2 times 4 plus 2 times 6 plus 2 times 7 plus 2 times 4 plus 2 times 1 and then plus 5. Now you could also, if you wanted to, you could have averaged the first and the second, but it would be, I think, a little bit more writing. 1/2 delta x is uniform. Add all the y values, so you should have 7 terms instead of 6, but notice all the ones on the interior doubled. Now the midpoint. Here's the deal with the midpoint. Because you're at the mercy of the data, you can't always create the values you need. So you won't always be able to do the midpoint from the table. But when you have a uniform delta x, you might be able to. What you need is at least the interval widths to be the same on consecutive intervals to be a true midpoint. So anytime you're asked to find a midpoint from a table of values, you're going to have to skip every other interval. Just realize that. So it's not really the best practice. So we're going to only get to use 3 intervals instead of 6. Here's why. What is the width from 0 to 1? It's 1 unit. But what value is halfway between 0 and 1? 1/2. How far is it from 1 to 2? It's 1 unit. And what's halfway between there? 1.5. How far is it from 2 to 3? It's 1 unit. And what's in the middle? 2.5. Okay, so here's what this would look like. Delta x is uniform now. My delta x is no longer 0.5. It's 1 because I have to skip every other interval. And now the y values that I'm using are the y values that are at the midpoint x value. So that's going to be 4, 7, and 1. So 4 plus 7 plus 1. Now, again, this is not the best practice in this case because there are other y values that we're omitting from this calculation. But they could certainly ask it. So just remember, for the midpoint, you have to skip every other one, and it has to be an even number of subintervals, and it has to be a true midpoint. All right, we'll stop there today. Tomorrow we'll do example 11. That's the one where the data is given, but they're unequal widths, and then we'll retreat back and talk about what's the difference between a definite integral and area, and how we can use one to find the other. All right, that's it. All right, have a super rest of your day. No 5 questions tonight. We'll pick that back up on Thursday. Oh, that's right. There is a review 7th period in here.